Assistant Professor in Andhra Pradesh State University's Electronics and Communication Engineering 2018 Question Paper Solutions Part 3, that is from question number 61 to question number 90. Question number 61. What is the condition to saturate BJT? So transistor is in saturation if IB base current greater than or equal to IC saturation by HFE. HFE is forward current gain. Beta DC is also forward current gain. Rearranging this expression, we will have IC less than or equal to beta IB, or IB greater than IC saturation by HFE. These are the conditions for transistor to enter into saturation. Correct option is 4. IB greater than or equal to IC saturation by beta DC. Question number 62. In junction field effect transistor, drain current in constant current area increases. Let us see the characteristics and regions of JFET. These are the drain characteristics of junction field effect transistor. The x-axis is VDS, y-axis is drain current in milliampere. Saturation region or pinch off region, ohmic region in the curve from 0 to point, from origin to point A, it is ohmic region or linear region. Beyond point C, it is breakdown region. And these characteristics are obtained for while keeping VGS is equal to constant. Let us see the characteristics of P channel JFET and N channel JFET. In P channel JFET, from the characteristics of P channel JFET, the drain current in constant current area, the drain current, this is the drain current. So drain current in constant current area, this saturation region have constant current. Drain current in constant current area increases if gate source bias voltage decreases. Gate source bias voltage decreases. So if it is plus 4, this is a drain current. For plus 3 volts, drain current. For 0, this is a drain current. If gate source voltage VGS decreases, then drain current is increasing. Similarly, from the characteristics of N channel JFET, drain current in constant current area increases. So drain current is increasing if the magnitude of VGS gets decreased. Magnitude of VGS gets decreased. If the magnitude of VGS gets decreased. So from both the characteristics of P channel JFET and N channel JFET, drain current increases if VGS gets decreased. Correct option is 1. Question number 63. An N-channel depletion MOSFET with positive VGS is operating in the. So generally, this depletion MOSFET has two modes of operation. One is enhancement mode and depletion mode. These are the two different modes of operation with depletion MOSFET. Depletion MOSFET can operate in enhancement mode if VGS is positive or VGS greater than 0. It operates in enhancement mode. If VGS is negative, then depletion MOSFET operates in depletion mode. So let us see in N-channel depletion MOSFET, if VGS is positive, gate source voltage is positive, the mechanism is more electrons are attracted into the channel, which increases the conductivity of the channel. As VGS further increases, it accumulates more and more electrons into the channel. Hence, drain current increases. Here, drain current is greater when compared to ID at VGS is equal to 0. That is, drain current is greater than IDSS for VGS is equal to 0. This mode of operation is called enhancement mode. This mode of operation is called enhancement mode of operation. In depletion MOSFET, the channel is continuous. The channel is continuous and it can be operated with bipolar input signal. In depletion mode, the channel is continuous and it can be operated with bipolar input signals, that is positive VGS or negative VGS, irrespective of the doping channel. Hence, it is also called dual mode MOSFET. If VGS is negative, the channel repels the electrons and attracts holes from the substrate. Hence, the number of electrons in channel decreases, thereby decreasing the conductivity. The drain current ID decreases. Here, the drain current ID is less when compared to ID at VGS is equal to 0. That is, ID less than IDSS. This mode of operation is called depletion mode. This is a mechanism happening in depletion mode. If VGS applied gate source voltage is positive, it operates in enhancement mode. If applied gate source voltage is negative, it operates in depletion mode. In depletion mode, drain current, this is a drain current in depletion mode, it decreases. This value is less than ID is equal to IDSS at VGS is equal to 0. In enhancement mode, drain current is greater than IDSS when VGS is equal to 0. This is the symbol for P channel and N channel depletion and enhancement mode MOSFET. In enhancement mode MOSFETs, the channel is discontinuous, whereas in case of depletion MOSFET, the channel is continuous and it can be operates in both depletion mode and enhancement mode. Hence the name dual mode MOSFET. So here the correct option is when VGS is positive. Given in the question, VGS is positive, then it operates as enhancement mode MOSFET. If VGS is negative, for negative VGS, it operates in depletion mode. The other name for depletion MOSFET is dual mode MOSFET. Correct option is 1. Question number 64. Emitter follower. It is an example of. So let us see different feedback networks. Voltage series feedback or voltage amplifier, series shunt feedback amplifier. The examples of voltage series feedback are common collector amplifier, common or it is also called emitter follower, common drain amplifier or source follower, closed loop non-inverting amplifier. Examples of voltage series feedback. Examples for Examples for current series feedback network or series feedback network or transconductance amplifier is common emitter amplifier or common drain amplifier. Similarly, for voltage shunt feedback network or shunt feedback network or trans resistance amplifier is collector to base biasing closed loop inverting amplifier. Then example for current shunt feedback network or shunt series feedback network Our current amplifier is cascading amplifier. In the question, emitter follower. Emitter follower is, it is also called common collector. Emitter follower or common collector. So correct option is voltage series feedback. Option 4, or voltage amplifier or series shunt feedback network. Question number 65. The slope of transfer characteristics of JFET is equal to. So we know that the transconductance or mutual conductance or figure of merit is equal to the slope of transfer characteristics. Slope of transfer characteristics is nothing but a transconductance or mutual conductance or figure of merit of junction field effect transistor. In JFET, the drain current expression ID is equal to IDSS 1 minus VGS by VP whole square. If gate source voltage is 0, if this gate source voltage is 0, then ID is equal to IDSS. The formula for transconductance is dID by dVGS. Differentiation of drain current with respect to gate source voltage, keeping drain source voltage constant. This is transconductance or slope of transfer characteristics. So from this, keep this ID expression in this transconductance expression. GM is equal to dou by dou VGS, and ID is replaced with IDSS 1 minus VGS by VP whole square. And then differentiation with respect to gate source voltage, we will obtain minus 2 IDSS by VP 1 minus VGS by VP. These are transconductance. Unit of transconductance is mho. Keep VGS is equal to 0. So in this expression, keep this VGS is 0. Keep VGS is 0. Then GM is equal to minus 2 IDSS into 1 minus 2 IDSS by VP. So that is, bring minus 2 to the denominator. Transconductance GM is IDSS by minus VP by 2. This is for linear approximation, and this slope is calculated at midpoint of transfer characteristics curve. So let us see the transfer characteristics curve. So in this curve, it is drawn between VGS on x-axis and drain current on y-axis, keeping VDS as constant. Keeping VDS as constant. So in this curve, at VGS is equal to 0, this is a point where VGS is 0. At VGS is equal to 0, drain current ID is IDSS. At VGS is equal to V minus VP, drain current is 0. Here drain current is IDSS. Here the drain current is 0 amperes. At midpoint, assuming this graph as a linear graph, under the midpoint, drain current, the slope is minus VP by 2. So correct option is 2. The slope of transfer characteristics of JFET is equal to minus VP by 2. And this slope is obtained assuming the curve is a linear and the slope is calculated at midpoint of transfer characteristics curve. Question number 66. The input impedance of MOSFET is. So let us see the input impedance of MOSFET, BJT and JFET. The gate leakage current in metal oxide semiconductor field effect transistor is in the order of 10 power minus 12 amperes. It is in the order of 10 power minus 12 amperes. Therefore, input resistance of MOSFET is in the order of 10 power 10 ohms to 10 power 15 ohms. This is the order of input impedance. Gate leakage current is lower, input impedance is higher. Similarly, the gate leakage current in junction field effect transistor is in the order of 10 power minus 9 amperes. Therefore, input impedance is in the order of 10 power 8 ohms. Now, the input impedance of As leakage current is less in MOSFET, input impedance is high in JFET. Therefore, input impedance of MOSFET is much higher when compared to input resistance or impedance of JFET. Similarly, input resistance of JFET is greater than BJT. Therefore, from these 2 points, the conclusion is input impedance in MOSFET is greater than JFET greater than BJT. So correct option is 2. Input impedance of or input resistance of MOSFET is higher or more than that of BJT and FET. Question number 67. CMOS devices use. So CMOS stands for complementary metal oxide semiconductor field effect transistor is obtained by connecting PMOS, that is P channel MOSFET, and NMOS, N channel MOSFET, and these are connected in series. So this is PMOS, P channel MOSFET, N channel MOSFET, and these are connected in series. Gates are tied to form a common input. It results in CMOS. Complementary metal oxide semiconductors are those devices in which both P-type and N-type enhancement MOSFETs are diffused onto the same chip. Correct option is 2. CMOS devices use complementary E MOSFETs. Question number 68. In the fabrication process, the Bridgman technique is used to grow gallium arsenide crystals. So this Bridgman technique are used to grow the gallium arsenide crystals, whereas Czech-Jorlowski method and float zone crystal techniques, it is used in growing silicon crystals. For growing silicon crystals, float zone technique or Czech-Jorlowski technique, whereas for growing gallium arsenide crystals, Bridgman technique. Correct option is 4. Question number 69. In wafer preparation, the purified SiHcl3 is used in hydrogen reduction to prepare the dash. So the answer is electronic grade silicon. So let us see step by step procedure. Initially, the starting material in silicon wafer preparation is relatively pure form of sand, which is also called quartzite. SiO2. This quartzite is placed in a furnace with various forms of carbon. The overall reaction will be like this: silicon carbide, which is a solid, silicon dioxide, SiO2, which is a solid, that is quartzite, kept in a furnace heated at a temperature of 2000 degrees centigrade. It results in silicon liquid, SiO gas, and carbon monoxide, which is a gases. This above reaction produces metallurgical grade silicon. In first step, we will obtain metallurgical grade silicon, MGS, which is 98% purity. Then this MGS, metallurgical grade silicon, is pulverized and treated with hydrochloric acid at 300 degrees centigrade to form trichlorosilane, SiHcl3, or trichlorosilane. This purified trichlorosilane is then used in hydrogen reduction to prepare electronic grade silicon, EGS, electronic grade silicon. EGS is a polycrystalline material of high purity and is used as a raw material in preparation of IC fabrication. This EGS is 99.999% pure polycrystalline silicon, and it is used as a starting material for the crystal growth. In the question, which of the following in wafer preparation purified SiHcl3, that is trichlorosilane, used in reduction reaction to prepare the electronic grade silicon? Initially quartzite, and then electronic grade metallurgical grade silicon, and then EGS, electronic grade silicon. To prepare this EGS, so from MGS we need to go for the hydrogen reduction technique using SiHcl3. Correct option is 1, electronic grade silicon, which is 99.999% pure polycrystalline silicon, which is a raw material for preparation of integrated circuits. Next question. In epitaxial growth, silicon wafer is placed in a graphite board and to be heated about the temperature of more than 1200 degree centigrade. So for crystal growth process to take place, the silicon is heated above 1200 degree centigrade. This epitaxial growth is a process which is used to grow thin crystalline layer. This is thin crystalline layer on a crystal substrate. In epitaxy process, substrate wafer acts as a seed crystal. Next question. The given circuit, the circuit given in the figure acts as a, obviously capacitor and diode is here. It acts like a clamper circuit. So clamper circuit are DC restorer or DC reinserter, and this is a clamper circuit without any bias. The given circuit is clamper circuit without any bias, no positive bias or negative bias. So let us see the wave circuit diagrams for half wave rectifier. So half wave rectifier consists of a diode and load resistor, input output waveforms of half wave rectifier. Next is positive clamper circuit, capacitor, diode positive is connected to ground. This is positive clamper circuit. In positive clamper circuit without any bias, and this is negative clamper circuit. Negative part of diode is connected to ground without any bias. Given circuit is negative terminal of diode is connected to ground. It is also called, therefore given circuit is negative clamper circuit without any bias. Next is envelope detector. This is a circuit diagram for envelope detector. And circuit diagram for clamper consists of resistor and diode. Shunt clamper without any reference voltage, shunt clamper with positive reference, and shunt clamper with the negative reference voltage. Okay. Correct option 2. Question number 72, and this question is deleted from the question paper. In the given question, which is a clamping circuit, the value of current limiting resistor is obtained. Current limiting resistor should not be large or should not be small. For proper clamping operation, the value of current limiting resistor is square root of Rf into Rr. That is diode resistance in forward bias and diode resistance in reverse bias. In the given question, the forward resistance Rf is 250 ohms and the reverse resistance is 100 kilo ohms. Now the value of current limiting resistor R is equal to under root of resistance in forward bias, resistance in reverse bias, that is 100 into 10 cube into 250, that is 225 into 10 power 6 under root. Its value is 5 square into 10 cube, 5 kilo ohms. The current limiting resistor R is equal to 5 kilo ohms. But the value of resistance across the diode we can correct the load also. In the question he did not mention current limiting resistor, hence this question is deleted. But the correct answer is 5 kilo ohms. Next, question number 73. This question is also deleted from the question paper. The ripple factor of power supply is a measure of purity of power output. So here he did not mention ripple factor of DC power supply. So the statement is vague, hence this question is deleted. But we know the ripple factor is the amount of AC present in the output of rectifier is called ripple. Ripple factor is defined as ratio of RMS value of AC component to DC component. And the ripple factor in half wave rectifier is gamma. Ripple factor in half wave rectifier is 1.21. Ripple factor for full wave rectifier, whether it is center tapped or bridge type full wave rectifier, it is 0.48. By using filters, the ripple factor will further decreases. Question number 74. In common emitter amplifier, the effect of RE is to increase. This common emitter amplifier with unbypassed emitter resistor increases the input impedance or input resistance by 1 plus HFE into RE times 1 plus HFE into RE times output resistance increases, voltage gain decreases. This common emitter amplifier with unbypassed emitter resistor decreases the voltage gain but increases input and output resistance. Let us see the statement 1. In common emitter amplifier, the effect of RE is to increase the input resistance because feedback quantity is voltage. Statement is correct. Since it is a current series feedback amplifier, this CE amplifier is example for current series feedback amplifier or series topology, series feedback topology, or transconductance amplifier or current sampling voltage mixing topology. In transconductance amplifier, current sampling or loop sampling, feedback network is connected in series with the output. Feedback network is connected in series with the output. Voltage mixing or series mixing. Voltage mixing or series mixing at the input. The feedback network is connected in series with the input. This series mixing increases the input resistance of feedback amplifier and current sampling increases the feedback resistance of feedback amplifier. So correct statement 1 is correct. In a common emitter amplifier, the effect of RE is to increase the input resistance because both input and output currents flow through RE. So statement 2 is also correct. Both statement 1, statement 2 are correct. Voltage mixing, series mixing, feedback network is connected in series with the input. This series mixing increases the input resistance. Question number 75. Which one of the following is not a characteristics of common emitter amplifier? So this common emitter amplifier, CE amplifier, produces 180-degree phase shift between input and output. Here current gain is high, voltage gain is high. Obviously, the product of current gain and voltage gain, that is power gain, is also high. Input impedance is moderate, output impedance is also moderate. From the given options, the current gain is low. So this is not a characteristics of CE amplifier. So current gain is high for CE amplifier. Question number 76. The temperature stabilized biasing is one of the applications of current mirror. Let us see the current mirror circuit, the basic BJT current mirror circuit. On the formulas of this current mirror circuit is given. The formula for I reference the formula to calculate collector current IC. Now, the advantages of constant current source or current mirror circuit are it provides very high emitter resistance, requires less components than constant current bias, simple design, easy to fabricate with properly matched transistor, collector current thermal stability is achieved. So collector current thermal stability is achieved. Temperature stabilized biasing, that is thermal stability, is one of the applications of current mirror circuit. So the statement given is true. Question number 77. Find out the correct option based on the below statements. H parameters do not vary with frequency. So statement is correct. This H parameter model is commonly used. So this is also correct, but is not a true reason for the statement 1. So let us see why. Because that from the advantages of H parameters are real numbers up to radio frequencies and they do not vary, or the H parameters does not vary with frequency. H parameters are easy to measure, easily convenient to use in the circuit analysis and design, easily convertible from one configuration to other configuration. They are determined from the transistor static characteristics curves are readily supplied by the manufacturers. Due to these advantages of using H parameters in describing a transistor, H parameter model is commonly used. Because of these advantages, easy to measure, obtained from the transistor statistic curves, easily convertible from one configuration to other configuration, convenient to use in circuit analysis and design. These are the advantages of H parameters. Due to its advantages of using H parameters in describing the transistor hybrid model or H parameter model is commonly used. So statement 1 is correct and 2 is not a valid reason for the statement, true reason for the statement 1. Question number 78. The voltage gain of common collector circuit is, if the common collector circuit is ideal, voltage gain is 1. If the circuit is practical, it is less than 1. So it is around 0.99 something. Hence, common collector amplifier is also called voltage buffer. So both options are correct. Option 2 and option 3 from the key. Question number 79. Given feedback connection type is. So in the given network, the feedback network is connected in parallel at the output of forward path network implies it is voltage sampling or node sampling. The feedback network is connected in parallel at the input of forward path network. So if it is connected in parallel at the input, it implies current mixing or shunt mixing. This is a feedback network connected in parallel to the output, connected in parallel with the input. So this is voltage sampling current mixing feedback network or voltage shunt feedback network, shunt feedback amplifier or trans resistance amplifier. Therefore it is correct option is 2, voltage shunt feedback network, voltage shunt feedback network or shunt feedback network or trans resistance amplifier or voltage sampling current mixing feedback network. Question number 80. Voltage feedback decreases the output impedance, that is statement 1. So voltage feedback or voltage sampling or node sampling decreases the output impedance, of feedback amplifier. Current feedback or current sampling or loop sampling increases the output impedance of feedback amplifier. Therefore statement 1, statement 2 both are correct. Correct option is option 3. In series mixer, signal is voltage signal. Series mixing increases the input impedance. Shunt mixer, signal is current signal. Shunt mixing decreases the input impedance. Question number 81. In a crystal oscillator, the frequency of oscillations remains substantially constant. So the above statement is true. Option 1 is correct. Crystal oscillator is a fixed frequency oscillator. A good crystal oscillator provides excellent amplitude and frequency stability of oscillations. If crystal thickness changes, the frequency of oscillation changes. But for a fixed thickness of the crystal, the frequency of oscillations produced by the crystal oscillator is remains substantially constant. Next question. The crystal oscillator produces frequencies in microwave region. Correct option is 2. This Hartley oscillator, Colpitts oscillator and Clap oscillator, Hartley, Colpitts and Clap, these are radio frequency oscillators, whereas Windbridge oscillator, RC phase shift oscillator are audio frequency oscillators. The crystal oscillator produces very high frequency radio waves and then a portion of microwave frequency waves. Which of the following is a true demerit of negative feedback amplifiers? So this negative feedback amplifier or degenerative feedback, negative feedback or degenerative feedback increases the bandwidth. It is increasing higher cutoff frequency, decreasing lower cutoff frequency. Obviously, bandwidth is increasing, and then it decreases the distortion and noise by a factor of 1 plus A beta. Negative feedback decreases distortion and noise, increases input impedance, decreases output impedance. But because of negative feedback, gain decreases due to negative feedback. Gain decreases due to negative feedback, which is a true disadvantage. Here, which of the following is a true demerit? So true demerit is reduction in gain. Question number 84. So it is related to common mode rejection ratio. The common mode rejection ratio, it is a ratio of differential mode gain to common mode gain. Higher the value of common mode rejection ratio, better is the operational amplifier. The relative sensitivity of an op amp to a different signal as compared to a common mode signal is called common mode rejection ratio. This is a definition of CMRR. The relative sensitivity of operational amplifier to a different signal as compared to the common mode signal is called common mode rejection ratio. In the question, given common mode rejection ratio is 60 dB, that is 20 log x, 20 log common mode rejection ratio base 10 is 60 dB. So from this common mode rejection ratio is 60 by 20, that is 30. 60 by 20 is 3, 10 power 3. So common mode rejection ratio is 1000, and then given differential gain. So differential gain is 1000. Differential gain is 1000. We need to calculate the common mode gain. Common mode gain is equal to differential gain, that is 1000 by CMRR, common mode rejection ratio to 1000. Its value is 1. So common mode gain is 1. So correct option is option 2. It is not option 1, it is option 2 is correct as per to the given data. Next question. Assume source and drain terminals of MOSFET are tied together and it is used as a two terminal device, then arrangement will work as a capacitor. In a MOSFET, N channel depletion MOSFET or N channel enhancement MOSFET or P channel depletion MOSFET or P channel enhancement MOSFET, if drain and gate are connected together, if drain and gate are connected together, then it acts like a active load or load MOSFET, then it acts like a resistor. In a MOSFET, if drain and source are connected together, then it acts like a capacitor. So here in the question, the drain and source terminals are connected together. It acts like a capacitor. If drain and gate are connected together, then it acts like a resistor. Correct option is 2. Next question. The hybrid notation for reverse open circuit voltage amplification in small signal equivalent circuit is. We know the definition for hybrid parameters are V1 is equal to H11 I1 plus H12 V2, I2 is equal to H21 I1 plus H22 V2, where I1 V1 are input voltage, input port voltage and current, I2 V2 are output port voltage and current. For common emitter configuration, input is base, output is collector. So input is base means input voltage is base voltage, input current is base current. Output collector means output voltage is collector voltage, output current is collector current. For CE configuration, the H parameter model can be given as VB is equal to HIE. So E stands for common emitter. If it is collector means HIC. If it is base means HIB. Common base means HIB. HIE into IB plus HRE into VC. IC is equal to output current is equal to HFE IB plus HOE VC. This HI, HR, HF, HO becomes in CE configuration becomes HIE, HRE, HFE and HOE, where HR is reverse voltage gain, HF is forward current gain, HI is input impedance, HO is output admittance. Therefore, the correct option is VB is equal to HIE into IB plus HRE into VC, that is input voltage, input output current I2. So I2 is output. So output current I2 in common emitter is, that is collector current. Collector current IC is equal to HFE IB plus HOE VC. Correct option is 2. In CE configuration, the hybrid model voltage current characteristics represents. So that is VB. So VB means input voltage. VB is equal to HIE IB plus HRE VC. So this 87 question and 86 question almost same. Correct option is 2. Next question number 88. So given RE is 100 ohm, small RE is 10 ohms, beta AC is 150. The AC input resistance at the base is. So for CC amplifier, input resistance RIB, given it is CC amplifier, input resistance RIB is equal to R pi plus 1 plus beta R naught parallel to capital RE, where R pi is input resistance between the base and the emitter, R forward diffusion resistance of base emitter junction, R naught is output resistance of transistor model, VA by ICQ. VA is early voltage, IC is Q is quiescent collector current. Capital R is emitter resistor, that is externally connected. R pi formula is VT into beta by ICQ, that is beta by GM or beta into small RE. Small RE is a AC resistance of forward bias base emitter junction. These are the formulas used to calculate the AC resistance. Given RE is capital RE, the resistor connected externally is 100 ohms and small RE is 10 ohms, beta AC is 150. Now RIB is approximately equal to R pi. So R pi value can be calculated as beta small RE dash. So that is beta is 150 into 10. So R pi is 150 into 10 plus 1 plus beta. So 1 plus 150 1 plus 150. Small r naught, generally small r naught far greater than re, that is r naught parallel to capital re is approximately equal to re. Keep it as re. Re is emitter resistor is 100 ohms. So this is 1500 plus 151 into 100. So this RIB is 16600, that is 16.6 kilo ohms. RIB, it is 16.6 kilo ohms. Correct option is 2. Next, question number 89. For a given circuit VB1, this VB1 voltage is 5 volts, VB2 voltage is 7 volts. If the cut-in voltage of diode is 0.7 volts, then positive peak and negative peak output voltages are. This is a two-level clamper circuit. Given two-level clamper circuit, VB1 is 5 volts and VB2 is 7 volts, and the cut-in voltage for each diode is 0.7 volts. V gamma is 0.7 volts. Now let us see case 1. If Vi, this input voltage, is greater than VB1, then diode D1 is on, D2 is off. If diode D2 is off, output volt, it is a open circuit. Diode D2 is off means it is open circuit. This is like this. D2 is off means open circuit. Now the output voltage is V gamma plus output voltage V0 is equal to VB1 plus V gamma. So VB1 is 5 volts, V gamma is 0.7 volts, it is plus 5.7 volts. Next, case 2. If input voltage Vi less than VB2, then diode D1 is off, open circuit, D2 is on, output voltage V0 is equal to minus of VB2 plus V gamma. Apply KVL in this outer loop. Here apply we need to KVL for case 1. Then output voltage V0 is equal to minus of VB2. VB2 given is 7 volts and V gamma is 0.7 volts. Now it is minus 7.7 volts. Next, case 3. If input voltage lies in between VB2 and VB1, then diode D1 is off, D2 is off, output voltage same as input voltage. For case 1, input voltage greater than VB1. Case 2, input voltage less than VB2. So the output voltages are 5.7 and 7.7 respectively. If in the question, if input voltage lies in between VB1 and VB2, then what is the output voltage? Output voltage is same as input voltage. Correct option is 3. Next, question number 90. Given R1 is equal to R3 is equal to 1 kilo ohm and R4, R2 are 3 kilo ohms. This R4 and R2 are 3 kilo ohms, R1, R3 are 1 kilo ohm, input resistors are 1 kilo ohm, and V11 is 3 volts, V12 is 2 volts. What is the output voltage? So the given circuit is a differential amplifier circuit, and this circuit is designed by using operational amplifier, differential amplifier using op amp. V1, V2 are the input voltages applied to inverting input terminal and non-inverting input terminal respectively. Here the output voltage, the condition for output voltage is V0 is equal to R2 by R1, V2 minus V1, and this output voltage is condition is satisfied if R2 by R1 by R2 is equal to R3 by R4. Here R1 by R2, R1 by R2, that is 1 by 3 is equal to R3 by R4, 1 by 3. The condition is satisfied, then output voltage is V0 is equal to output voltage V0 is equal to R2 by R1. So R2 is 3 kilo ohms, R1 is 1 kilo ohm into V2 minus V1. So V2 is voltage applied to the non-inverting terminal. So here it is 2 volts and voltage applied to inverting terminal is 3 volts. So 3 into minus 1, output voltage is minus 3 volts. The output voltage for the given differential amplifier is minus 3 volts. Correct option is 4.